Most people think space is empty and safe. The reality is terrifying. The universe produces explosions so powerful they could sterilize our planet from thousands of light years away. On December 27, 2004, a magnetar burst from SGR 1806-20 briefly became brighter than any object in the X-ray sky except our Sun. The burst caused significant ionization of Earth's upper atmosphere and disrupted radio communications for several hours. Tonight, 7 different cosmic events could trigger extinction without warning. Unlike asteroids we can track or volcanoes we can monitor, most cosmic threats travel at light speed. Detection equals arrival. No time for evacuation, no chance for deflection. These dangers operate on scales that dwarf human comprehension. Solar superflares could happen tomorrow. Galaxy-spanning explosions could unravel reality itself. Modern civilization's electromagnetic dependence makes us more vulnerable than any previous generation to cosmic violence. From local solar tantrums to vacuum decay that could delete the laws of physics, each threat follows different rules of probability and destruction. Some arrive with minutes of warning. Others announce themselves by obliterating everything in their path. The universe has been conducting these experiments in annihilation for billions of years. We just happen to be watching from the target zone. September 1, 1859. Richard Carrington witnessed something unprecedented while observing the sun through his telescope. A brilliant white flash erupted from a sunspot group. Within hours, telegraph systems worldwide began failing. Operators received electric shocks. Equipment caught fire. The most powerful geomagnetic storm in recorded history had begun. The Carrington event reached magnetic field disturbances estimated at 800 to 1700 nanotesla based on modern analysis. Aurorae appeared as far south as the Caribbean. People could read newspapers by aurora light in Boston. Telegraph lines sparked and failed across 2 continents. One operator in Boston continued sending messages for 2 hours using only the induced current from the geomagnetic storm. Today, a Carrington-class event would cause economic damage ranging from hundreds of billions to trillions of dollars. Power transformers would fail across multiple continents. Satellites would suffer permanent damage. GPS systems would become unreliable for weeks. The electromagnetic pulse would make the 1859 telegraph failures look trivial compared to our current dependence on electronic infrastructure. But the Carrington event might represent only a preview. The Kepler Space Telescope observed approximately 150,000 stars between 2009 and 2017. Analysis revealed that solar-type stars do produce superflares with energies 10 to 100 times larger than anything recorded from our Sun. These stellar explosions release energies of 10 to the 35th power joules in minutes. Frequency analysis shows superflares occur in solar-type stars approximately once every 2,000 to 5,000 years. The question dividing solar physicists is whether our specific Sun can produce such events. Some argue the solar magnetic field cannot concentrate sufficient energy for superflares. Others point to the Kepler data as evidence that any solar-type star, including ours, could generate these massive eruptions. No clear geological evidence exists for extreme historical solar events. Searches for radiation signatures and isotope production from solar neutron interactions have yielded ambiguous results. This absence could mean superflares never occur in our solar system, or it could mean they happen so rarely that detecting evidence in Earth's geological record remains statistically unlikely. A superflare twice the Carrington event's power would disable transformers across multiple continents for weeks to months. The biological effects would be modest due to atmospheric shielding, but technological collapse could disrupt agriculture, medical systems, and food distribution networks. Modern society would face cascading failures unlike anything in human history. Solar wind observations provide 10 to 20 minutes warning for coronal mass ejections. Grid operators could take systems offline during extreme events, but fundamental limitations persist. We cannot predict when our Sun might produce its most powerful flare. Gamma-ray bursts release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. These cosmic detonations come in 2 varieties. Long bursts result from massive star collapse. Short bursts arise from neutron star mergers. Both channel their energy into relativistic jets traveling near light speed. The jets have opening angles of only 5 to 20 degrees. Like cosmic laser beams, they concentrate devastating radiation into narrow cones. A moderate luminosity gamma-ray burst could deliver lethal radiation doses to planets within 100 to 1,000 light-years. The sterilization mechanism operates through high-energy photons stripping away atmospheric ozone and exposing surface life to deadly solar ultraviolet. WR-104 sits 8,000 light-years away in Sagittarius. This Wolf-Rayet star has shed its outer hydrogen layers, exposing a hot helium core. Evidence suggests the system possesses a narrow pole structure that might be aligned toward Earth. If WR-104 collapses and produces a gamma-ray burst, the geometric probability becomes critical. Even if WR-104 generates a gamma-ray burst, the chances of its narrow jet pointing at Earth are only a few percent. Stellar evolution models suggest the star could explode anywhere from decades to hundreds of thousands of years from now. The timing uncertainty spans 6 orders of magnitude. No observatory can predict which star will undergo core collapse. Gamma-ray bursts are detected only after their photons arrive at light speed. The Neil Gehrels Swift Observatory and Fermi Gamma-Ray Space Telescope identify these events within seconds of occurrence. But detection confirms the event rather than preventing exposure. The Milky Way produces approximately 1 gamma-ray burst per million years. Most jets point away from Earth due to random geometric orientation. Accounting for all factors, the probability of a lethal nearby gamma-ray burst in the next 1,000 years ranges from 1 in several million to 1 in tens of millions. The December 27, 2004 magnetar burst demonstrated smaller-scale versions of this threat. CETGR 1806-20 released enormous energy in 0.2 of a second. A magnetar burst from 10 light-years away could produce significant atmospheric ionization and ozone depletion. The nearest known magnetar sits 6,500 light-years away, providing comfortable safety margins for now. Supernovae release 10 to the 51st power ergs of energy. Unlike gamma-ray bursts, supernovae radiate energy in all directions. Proximity becomes the only factor determining lethality. These stellar explosions operate through ultraviolet and X-ray radiation, stripping atmospheric ozone rather than kinetic energy from expanding debris. A supernova within 25 to 100 light-years could cause 50% or greater ozone depletion. Surface organisms would experience deadly ultraviolet doses as the protective ozone layer rebuilds slowly. Ocean depths below 10 meters would retain significant ultraviolet shielding, potentially creating refuges for aquatic life. Betelgeuse represents the most famous nearby supernova candidate. This red supergiant sits 640 light-years away in Orion. Recent brightness fluctuations sparked speculation about imminent explosion, but evolutionary models suggest thousands of years remain before core collapse. Even if Betelgeuse exploded tomorrow, the distance places it outside immediate sterilization radius. Pegasi presents a different scenario. This white dwarf in a binary system sits approximately 100 light-years away. Mass transfer from the companion star accumulates material on the white dwarf surface. A thermonuclear runaway could trigger a Type 1a supernova. The timing uncertainty spans 100,000 years to several billion years. The Milky Way produces 2 to 3 supernovae per century based on historical records and remnant counts. With roughly 100 billion stars in the galaxy, the probability of any specific star exploding in any given year remains vanishingly small. A supernova close enough to damage Earth's atmosphere occurs roughly once every 100 million to 1 billion years. But consider the Chelyabinsk reality check, February 15, 2013. A 20-meter asteroid delivered 440 kilotons of energy with zero warning. The object remained invisible until atmospheric entry due to solar glare approach. Current asteroid surveys have found approximately 30% of an estimated 25,000 near-Earth asteroids larger than 140 meters. Apophis will pass within 32,000 kilometers on April 13, 2029. 140-meter impacts occur every 6,000 to 10,000 years. Kilometer-scale extinction events happen every 500,000 to 1 million years. Regional devastation remains the realistic near-term threat rather than species extinction. The detection gap for smaller objects creates genuine vulnerability windows. Millions to hundreds of millions of rogue black holes wander the Milky Way invisibly. These stellar corpses were ejected from their birth systems through gravitational interactions. They emit no electromagnetic radiation. Detection requires gravitational lensing or gravitational wave signatures from rare interactions with other massive objects. A stellar mass black hole passing within a few hundred to few thousand astronomical units could destabilize planetary orbits. The encounter probability within the next billion years approximates 1 in 1 million or less. Human timescale probability remains basically zero over thousands of years. Vacuum decay represents the ultimate cosmic threat. Quantum field theory predicts our universe might exist in a false vacuum state. If true vacuum nucleation occurs, a bubble of altered physics would expand at light speed. No detection would be possible. The bubble arrival would be instantaneous and absolute. Current scientific consensus treats vacuum decay as highly speculative. Probability estimates range from never to billions of years with no observational evidence. The threat represents not just extinction but erasure of physical possibility itself. Most physicists consider this scenario too theoretical for practical concern. Risk hierarchy places immediate threats like solar superflares and asteroid impacts as primary concerns. Detection capabilities continue improving through space-based telescopes that reduce solar glare limitations. Warning times vary dramatically. Solar events provide minutes. Asteroids provide weeks to months if detected early. The fundamental asymmetry persists. Cosmic threats traveling at light speed cannot be outrun or deflected after detection arrives. 7 threats operate on 7 different probability scales. Solar superflares could happen within decades. Vacuum decay may never occur. The detection paradox remains unsolved. Most dangerous cosmic events announce themselves by arriving. Our electromagnetic civilization faces threats that previous generations could survive through technological simplicity. Asteroid detection and solar weather monitoring represent actionable planetary defense strategies. The Carrington event of 1859 offers our best historical preview of near-term space weather consequences. Scientific monitoring continues improving through Kepler data analysis, magnetar observations, and enhanced asteroid surveys. Cosmic threats remain far less probable than terrestrial risks like climate change or nuclear conflict, but they persist as reminders of our cosmic context. We inhabit a dynamic universe where extinction-level events occur regularly throughout galactic history. Distance, probability, and vast emptiness provide our primary protection. Tonight, the universe continues its violent processes. Magnetars release energy bursts. Massive stars approach core collapse. Asteroids follow their orbital paths. Earth remains shielded by the same cosmic lottery that has protected life for billions of years. But as we extend our technological reach and electromagnetic dependence, one question grows more pressing. How do we prepare for threats that operate on cosmic timescales but could arrive at the speed of light without any warning at all?